Hey everybody, in this next video lesson we're going to talk about kinetic energy and temperature and how those affect intermolecular forces. Now first of all, we need to establish once again what temperature is. Temperature is the measure of the average kinetic energy of a system. When I say average, I mean you total up the kinetic energy of every particle in the system and divide by the number of particles and you get the average. Does that mean all the particles are traveling the same speed? Certainly not. Some are traveling faster and some are traveling slower in that system, which we will see shortly. But the average kinetic energy is the measure, but temperature is the measure of the average kinetic energy of a system. Well, what is kinetic energy? This is kind of a physics concept, but some of you probably already know that kinetic energy is the energy of motion. So in other words, as the particles are moving faster, the temperature increases. Take a look down here. We've got particles that are traveling faster as represented by the longer tails, and this means that they're warmer, whereas particles with shorter tails are moving slower. And the slow movement results in a lower kinetic energy, which means that they're colder particles. Let's bring this back around to intermolecular forces. Basically, particles are trying to be held together by the intermolecular forces. And the intermolecular forces in this case are never changing. They're constant. Like water's dipole-dipole interaction with other water molecules is constant. It doesn't get stronger or weaker. It stays consistent. But we can take ice and melt it into liquid if we can warm up the particles and make them move faster. And that, in effect, will break the intermolecular forces or weaken the intermolecular forces that are trying to hold the water molecules together. And so kinetic energy has the ability to weaken the effect of the intermolecular forces, but it doesn't actually change the intermolecular forces themselves. Intermolecular forces are always constant. So when you heat something up, you are breaking a molecule's ability to attract another molecule. Now I mentioned this already, but when you have a sample of solid or liquid or gas, and you're measuring the temperature of that solid or that liquid or that gas, the temperature is the average kinetic energy, not the energy of the individual particles. Each particle is traveling with its own speed, not an average, but a specific. Some particles are traveling faster than others. Some particles are traveling slower than others. I'm going to splice in a video now from another chemistry class that helps explain what the speed distribution looks like in a sample. Now, a quick word of note, this was recorded specifically to talk about gases, but this can be applied to solids and liquids likewise. So I refer to gases a lot in this next video clip, but it could include solids or liquids. What you see in front of you right now is a bell curve distribution of speeds of the molecules in a sample of gas. So across the horizontal, you'll see it increasing speed as you move to the right. Now up the left-hand side, there are no units, but this is relative fraction of the molecules. And so this bell curve shows you that some of the particles are traveling really, really fast. Some are traveling really, really slow, but then there's a peak or in the middle where the particles are, most of the particles, or the largest fraction of the particles, are moving that particular speed. Now, this symbolism up here is a little bit hard to understand, but I'll try and break it down for you, at least the ones that we care most about. This first one is MP, which stands for most probable. As you can see, it is the peak of the bell curve. So the most probable speed is the one where the highest fraction of molecules are traveling that speed. Now that last profile of speed distributions of particles inside a sample of gas was specific to a gas of known identity and at its temperature. But the speed profile will change when the temperature changes. It will also change with the molar mass of the particles. When temperature goes up, there will be less particles traveling at the average speed. And so the peak will get shorter, but there will be more traveling at higher speeds. And so the distribution of particles will shift slightly to the right. So in summary, when the temperature of a gas goes up, the peak gets shorter or more stout, but shifts slightly to the right. But when temperature goes down, the peak gets taller and shifts slightly to the left. Here is a graph, or actually two graphs, of the same sample of gas at two slightly different temperatures. What you're looking at in blue, or the cooler of the two, is the gas at 0 degrees Celsius. You see that it has a pretty high peak, and that peak lies somewhere right here we're going to increase the temperature of the gas. And a lot of times people think, well, you increase the temperature of the gas, well, you're going to shift the peak to the right because as temperature goes up, the speed should go up. But what you don't realize is that the particles spread out over a larger distribution of molecular speeds. And so we have a wider base bell curve. So it gets shorter and shifts to the right. It has to get shorter because we are spreading out the individual speeds over a wider range. So we have more particles traveling a higher speed at 100 degrees Celsius. Notice we have a larger fraction in the 100 degrees Celsius sample than we do in the 0 degrees sample. So we have more particles traveling a higher speed. But we conserve the number of particles. We don't have more total particles. So because we have an increased number of particles traveling at higher speed, then that means that the peak needs to decrease slightly. It's not as tall. But don't confuse a peak that's not as tall with a peak that's not as warm. But if you were to draw in using a different color, and I'll use green, what the peak would look like if the temperature of the gas dropped below 0, then you'd expect a very high peak coming up here, but it's going to be to the left of the 0 degrees Celsius peak, and it's going to taper off underneath the blue. So the peak shifted to the left because the temperature decreased. But you also have less particles traveling those warmer temperatures. You have a lower fraction, and since you have a lower fraction, well then we need to shift or distribute those particles into lower speeds. And so you have a higher number of particles traveling at lower speeds, which is what you would expect when the temperature drops. The bell curve shifts to the left and it gets taller. The last graph that I'm going to show you in this video lesson are all these different gases all at 25 degrees Celsius. Do you notice I've labeled the temperature down here? So they're all the same temperature, but they're not all the same speed distribution. What you'll notice is that the very, very light gases, in fact the lightest gas is hydrogen gas with a mass of 2. The molar mass, once again, of hydrogen is 1.01, but there are 2 of them, so it's 2.02. The lightest gas here behaves like a very hot gas. You see, it has a very low peak and a very wide range of speeds of its particles. Do you see it has a very, very small amount traveling a very, very high speed? But if you take the average of all of these particles, it would be the same temperature than the average of all of helium's particles. But see, helium doesn't have as many particles traveling those high speeds. And even the most massive of these gases listed here is oxygen. It is behaving like a very cold gas. It has a peak that's furthest to the left and tallest, but it has an incredibly small number of particles traveling those really, really high speeds. But that's because the higher the molar mass, it behaves more like a cold gas, where the lower the molar mass behaves more like a hot gas. So as we saw on the last slide, the speed of the profile changes when molar mass changes. At the same temperature, and all of those peaks that you saw on that last slide were all representing gas at the same temperature. They're all 25 degrees Celsius. But the distribution of speeds looked like they were different temperatures. But remember, it's the average. Those really light gases have a lot of particles traveling high speeds, but less particles traveling the average speed. Whereas the more massive particles have more particles traveling the average speed and very few to almost none traveling those incredibly high speeds. But if you take the average of all the particles, they would be the exact same because they have the same temperature. Heavier molecules have high fraction of their molecules traveling at that lower speed, which is why their peak is taller and shifted to the left. It's shifted to the left because they're less speedy and you have a higher fraction, which makes it taller. As molar mass goes down, the average speed increases, meaning the peak shifts to the right, even though you may have less particles traveling at that average speed. Let's bring it back to our notes here. So in summary, any sample of gas, there's a large range of particle speeds. That means that at any given moment, some particles are traveling the most probable speed, and some are traveling really, really fast compared to that, and some are traveling really, really slow. But the distribution curve shows all the particles and their average. So why does the temperature measure the average speed? Well, you factor in all the particles and all of their speeds at any given moment, and that represents the average or the temperature of the particles in that sample. Although the distribution of speeds may not be consistent over different ranges of temperatures, all of the particles underneath the curve contribute to the average kinetic energy, which we call temperature. You might be wondering, why the speed even matters. But this will make more sense when we start talking about vapor pressure, boiling point, and changing in state of matter. So I hope this helps. Well, that takes care of this video lesson. Thanks for watching.